Good morning, one and all. I'm SouryadharAutomata, working as an assistant professor in the Department of Computer Science Engineering at Mallareddy Engineering College for Women, Hyderabad. Today, I would like to give a brief introduction about formal language and automata theory. What is the necessity of formal language and what is the necessity of automata theory in the field of computer science is what we will be looking into this particular video today. Before getting into that particular concept, I would like to give a brief about what is finite automata. Basically, to talk about finite automata, we will talk about this particular word, which is automata. Automata means the abstract machines, or it is like a model for abstract machines. Now, what exactly is this model doing for abstract machines? And before that, what exactly are abstract machines? Abstract machines are something that help the user communicate the system with the system using the computational logic. It could be the compilers, it could be DBMS systems, or it could be the regression algorithms. Any which have a specific use of computation shall be coming under abstract machines. And these abstract machines will be working on series of states. Now, what exactly are those series of states? Now, in the very beginning, any particular process, there shall be there shall be two concepts. One is the input, the other one is an event. Input and an event. Now, what exactly is this process related to automata? This process could be of computational logic that can be resulting in a specific solution. Now, these series of inputs shall be becoming as series of inputs shall be the computational processes. Now, these computational processes at each state, and also as I am talking about series, we are also should be talking about the states. Each state shall be having computations done either on a particular series, or a particular series that is coming in the middle, or a particular series that is happening in the end. Now, basically, the graphical representation of automata can be done in three ways. One is the these are the three representation of automata, finite automata to be exactly, and these shall be talking about the graphical representations, shall be talking about graphical transitions, and also the tabular representations shall be talking about tabular transitions, and also the mathematical representations will be the combination of both graphical, tabular, and also some parts of calculus and some parts of principles of mathematical induction should be there in the process of transition. And talking about transitions, what is this transition? Assume that if there is a state transition. If there is a particular problem or a computational logic has to be developed for a problem of addition of two numbers, in the very first state it has to be 0. No numbers are there, no input is given. So this becomes the initial, and once the addition is done, we will be getting the sum at some, assume that this one is the nth step, and we will be getting sum. This becomes the final state. In between, whatsoever these states are occurring, they will be called as transitions, and they range generally from, if you take q as the number of states that are present pertaining to the given concept, then any given point of time, the initial state q1, q0 to qn will be the number of states from which each and every time, in each and every step, how many transitions are happening. That will be the transition of a problem from the beginning to the end. Now, before getting into the transition, we must be aware of the terminology that is present in the finite automata. Starting with the terminology, the first thing in the terminology is an alphabet. Now, what exactly is this alphabet? Basically, this alphabet is a collection of symbols, and these alphabets also constitutes to the characters. Let's see an example. If we take S to be an alphabet and A comma B are to be the elements that are present in this particular set S, then S is the alphabet, and these two together will be the characters. And how do we represent these is in this way, where S is the alphabet, A comma B becomes the characters of the set S, and so set S will become the character set. That means it is having some characters, and that's why it is an alphabet. And it could be something like a W, which is having 0, 1. This is also an alphabet set or a character set. The next one is string. Next terminology word is talking about string. Now, what exactly is this string? Now, in general, string means a series of characters, and we can say like it is a finite collection of symbols or characters. Yeah, and this particular string, the string which is housing the symbols or characters, is represented as in sigma, saying that this is the string and it is having some characters in it. So this becomes the string set, and these are the characters. Now, what could be the strings that can be obtained from this string set? Can be A comma A, B comma B, A B, B A, B A, B A B. These are the strings that can be obtained. And in the process of deriving a string, everything, like I said in the previous time, the transition should happen from the 0th position to the nth position. So even in the strings, we have one particular thing called epsilon, which means it is like, the epsilon is like null string. What does this null string do? Null string is the initial state in which the process starts to occur. Like if you if you add sum of two numbers, initially we must be taking two numbers. Before taking that, we will be declaring it as a void. So that void state is what the initial state is, the null state is. Now to represent that, what we do is sigma to the power 0, we will be getting the set of null set, which is epsilon. Now in this epsilon, as we progress to the number of states, it becomes sigma to the power 1, which is a comma b. Next it will be like sigma to the power 2, we will be getting a comma b, b comma a, and similarly sigma to the power 3, we get like a b, b a b, a b a, all these things, and till we reach sigma to the power k. And this is the completion of string. And we will now talk about a language. As we have seen alphabet, string, now we will be talking about language. Basically, in the language, what we talk here is we also take a string set, which is a comma b, and in this we try to list down the language in such a way where L can be how many times is A present and how many times is B present. For an example sake, I am taking here A power n comma B power n times, such that n is equals to 1. So the given from this, the obtained language shall be A B B A. This becomes the string, and this is the representation of language. And then let's see one final example of language, which is important, like how do we model the language. And this one is like L is equals to A power m B power n, such that here the condition is given in such a way where m is greater than n. This one is the logic given in such a way, and also n has to be only occurring twice in the formation of string. So how could the language model now? The language models in such a way m is greater than n, n is 2, and 2 refers to n, which is b. Now saying that b has to come 2 times and m has to be more than n. Certainly it can be 3, and similarly in this fashion too, and so on. This is another example of a language. So next concepts we will see in the next coming sessions. Thank you one and all for giving me this opportunity.